Good evening, Dr. Yong Wang. Am I audible to you?
Good evening, everyone. This is Yong Wang. Glad to be here.
Good evening, sir. How are you, sir? Hello, good evening.
Hi, Professor Rajeska. How are you?
Yeah, very fine, sir. How are you, sir? After a long time, we are meeting once again.
Sir, I'm afraid I cannot hear you. Can you hear me?
Yeah, it is clearly audible, sir. Very clear.
I saw you are speaking something, but let me see if there is some setting problem with.
Okay.
Somehow I cannot hear
But
anybody.
you are audible. You are audible. Oh. Mr. Madhusudan, can you please support Professor?
I'm making my voice the highest.
Yes, sir.
Everyone hear me?
Yeah, you are audible, sir.
Sir. Yes, sir, sure.
Sorry,
Professor Yong Wang, am I audible to you?
Should I log off and log in again?
That's better.
Please try it, sir. Please try it.
Yeah.
Let me try that. I cannot hear anybody somehow. I don't know what happened. Let me log in again.
Okay, sir.
Yes.
Okay, sir. Fine.
Good evening, Principal, sir. Good evening, sir. Yeah.
Hello? Can everyone hear me?
Hello. Yes, sir.
Sir, now we can check your audio. Like, am
Is
I
it
audible to you?
Audible to you, sir?
Madhu, is that right? I see
Yes,
your
sir.
voice is moving, but still I cannot hear somehow. This is strange.
Okay, I think there would be something
Let me use
related
the
to
chat
output
box.
settings.
It's clearly audible now.
Volume mixer. Let me check my volume mixer.
Dr. Wang, you are audible very clear. You may please continue. Start.
My volume is the highest for all the devices.
The problem is Professor Wang is not able to hear us, sir. That is the problem, I guess.
Then send a message.
Yes.
Rashekar.
Yeah, true.
He's
I sent
clearly
it
audible.
just now. I sent it.
He's clearly audible. He can start.
Let me try another computer. Let me see if I can log in from the other one. I'm using my laptop right now. Probably that's a problem. Sorry about this technical problem. Let me log in again.
Hello?
Yeah. Hello, sir.
Hello?
Hello,
Yeah,
sir.
hi.
Yeah, hi, sir.
So,
Can you
Yeah,
just hear
now it is
us
very
now?
clear.
yeah, it's very good right now. But I'm using a desktop computer right now. I don't
Okay.
have camera on this one.
Right, sir. Right.
Yeah, sorry.
Sorry,
Okay, sir.
sir.
Okay, okay. Right, sir.
Right.
Mr. Madhusudan,
Yes, sir.
please start a session.
Okay, sir. Sure.
Send a message that stating that you are clearly audible. You can start the session and introduce him.
Yeah.
Sure, sir. Sure,
Sir,
sure.
it is I have been sent and he will introduce, sir. No problem.
Okay. Introduce and send a message to him
Okay,
that you are clearly audible. You may please start.
Yeah.
Okay, sir.
Okay.
Fine. So, shall I start the session?
Yes, sir. Please start.
By message. You send by message.
Request
Everything
me.
by message.
I'll send it.
Okay. Good evening, one and all.
Yeah, good evening. Hi, how are you?
Yeah, very fine, sir. You are audible, sir, now.
Okay.
Right. Madhusudan, please start.
Okay. So I think we can start the session, sir. Yes. Good evening, one and all. Welcome you all for the session 7 of 5-day online faculty development program on sustainable solutions in hybrid vehicles, sponsored by AICTE and organized by Mangalore Institute of Technology and Engineering. The session 7 is of the topic Computer Vision Aided Autonomous Navigation System for using overhead cameras and Raspberry Pis in electrical vehicles by Dr. Yong Wang. So I welcome all the professors from the various esteemed universities and institutions for the session. I take this privilege to introduce Dr. Yong Wang for all the participants present in the session. Yong Wang received a PhD in Industrial Engineering and Operation Research from University of Illinois at Chicago in 2015. He also received a PhD in Energy and Power Engineering from Huzhang University of Science and Technology, China in 2010. He was a visiting scholar in the Department of Mechanical Engineering at the University of Michigan, Ann Arbor 2007 to 2009. He is currently an assistant professor in the Department of System Science and Industrial Engineering, Watson School of Engineering and Applied Science, Binghamton University. Dr. Wang's research at Binghamton University focuses on the design, modeling, and management of complex systems, healthcare, energy, and manufacturing. The central research team is to understand the working principles of this system and make them more efficient, reliable, cost-effective, and sustainable by optimally integrating various resources such as time, space, people, finance, information, equipment, and materials. Dr. Wang has published 55 peer-reviewed journals and conference papers in industrial and system engineering. He teaches operation research, project management, advanced energy engineering systems, engineering economics, computer programming, and ISc in healthcare at Binghamton University. Dr. Wang is a member of Institute of Industrial and System Engineering, the American Society of Mechanical Engineers, ASME, and the American Society of Energy Education, ASEE. He is the chair of the Quality and the Reliability Technical Committee in the Manufacturing Energy Division, MED, and ASME. He was an invited panelist for funding agencies such as National Science Foundation, NSF, and the Department of Defense DoD. He also served as a reviewer for the numerous prestigious journals and international conferences. It's our department privilege to have you for this particular session, sir. I welcome Dr. Yong Wang for this session, and it's over to you, sir.
Okay, thank you, everyone. I really appreciate your patience with me. Let me try to share my computer screen.
Sure, sir.
Is there a button I should click to share a screen, or I should present or something like that?
So you can, no, sir, exactly beside the screen will be having a present
Oh, okay, I see present now.
now
Okay,
option. You
can
can
I do
just
that?
click that and click entire screen so that your screen will be visible for us.
Okay, very good.
Yeah.
Okay, I'm sharing screen. Can everybody see the slides? Can everybody see the slides right now?
Yes, sir. Now it is visible. It is
Okay.
visible clearly, sir. Yeah.
Okay, very good. Thank you very much. Okay, thank you, everyone. Sorry about the technical difficulty. I'm right now switching to a desktop computer. So this one doesn't have a camera, but I think the voice should be fine. Today's talk, the topic is computer vision aided autonomous navigation
Okay,
system using an overhead camera and a Raspberry Pis. By the way, did anybody hear any echo or any volume problem, or is the sound okay? Is the voice okay for everyone, or is there any echo about this?
It is perfectly okay, sir. Please continue.
Okay, thank you very much. So this is a brief outline of today's talk. I put the acknowledgement first. So this is my habit. Then I'll introduce the research objectives and also the methodology we are using for this research. After that, I'll introduce a little bit about the hardware and software, and especially the camera, the Raspberry Pi system, driver, and robot car. After that, I'll introduce the system connection and wireless communication between the overhead system and the ground system. Then I'll introduce the process we have gone through to make the system autonomous. And after that, I'll make the conclusion and also the future work. So first of all, I would like to thank WISE, which is an individual institution in Watson College. It's called Watson Institute for System Excellence, especially Dr. Hari, who is also the dean of Watson College. He is a director of WISE. He sponsored this research. System Science Industrial Engineering Department, which I'm affiliated with. Dr. Kasane, who is the chair of SSIE, is also the associate director of WISE. They jointly funded this project for the students who work on this project. This is actually a termination project in our department. In our department, in the master program, we have industrial and system engineering. We also have a system science program. This is a student, Chen Xiu-Ai. She is a master student and pursued the capstone project option in our department. Actually, there are two two options for the master students. One option is that the master student, they can take courses and write a thesis. Another option is that they can take the courses and also finish a capstone project. Then they can graduate. This student just took that capstone project option, and this is actually my assignment to her. And at that time, she was a graduate research associate at WISE and also SSRE department. Last but not least, I would like to greatly thank MITE for giving me this opportunity to present it here. I think this is probably already the second time for me to participate in this kind of events. It's really my honor to be with you. I really want to thank Principal Prasad, Vice Principal Rajeshkar, and also all the other department heads for being here, and also the students and other faculty members. So autonomous systems have a lot of different kind of definitions. Most of people, when they talk about autonomous systems, they just think about self-driving cars. Of course, this is the most famous application, but autonomous system can be defined in many other aspects as well. It can be a self-driving car. It can be a drone flying around by itself. These drones can be military drones. It can also be for civilian purposes like last mile delivery. It can also be a robot. It can autonomously accomplish a mission by itself without too much interaction with human beings. These are all typical application of autonomous systems. So here we are trying to introduce one type of autonomous system using computer vision. And the specific application area is for indoor warehouses. We are planning to use this one for warehouse material distribution. So it can somehow help people move maybe heavy equipment or heavy devices from one place to another places. So what we are trying to do is that we're trying to use artificial intelligence, especially computer vision algorithms, and try to identify different type of obstacles and objects. Then based on the observation, we try to plan the best path from one place to another place and accomplish the mission by itself. So as I mentioned, this is a capstone project we assigned to a master student. In our system science industrial engineering department, we focus a lot on the integration of different components of the system together so they can actually work as an entire system. So we make assignments with specific objectives or guidelines. Then it's up to the students to carry out all these missions or tasks by themselves. We only provide occasional guidance. We will not do any coding for the students. It's all up to them to design the hardware, implement the hardware, connection, everything, and also programming, and finally make the system work and demonstration. So my requirement for the student is just these 6 points. So first of all, the system should be able to identify the vehicle and also obstacles in real time through an overhead camera. And then the system should be able to plan and track the optimum path for the vehicle or for the robot car to move on the ground. They should be communicate wirelessly between the overhead system and also the ground system. And we try to navigate the robot car from point A to point B while avoiding all these obstacles it can detect. And we do not want to use fancy sensors. We only try to use cheap, low-cost cameras. And using that, we try to develop a low-cost prototype system from scratch. So basically, the student cannot rely on any existing system. She has to finish everything, including all the coding from the basics. After the requirements are done, the student came up with this design. So this is a system design with overhead system and the ground system. The overhead system, we have a Raspberry Pi, we have a camera. They are connected together. The camera will capture what is going on the ground, especially inside a warehouse. Like we have static objects like boxes, pallets, totes, or even workers. or maybe forklift trucks. Some of them are static objects, others are moving objects. So after the scene is captured, it sends the information to the Raspberry Pi. The Raspberry Pi will in real time process all this information and try to identify different type of objects on the ground. And then it will send the information, it will do the path planning, which is the best path. After that, it will send the waypoints of those passes to the ground system wirelessly. You can see that the ground system will have another Raspberry Pi. And this Raspberry Pi will receive all these waypoints, and then it will connect it to the drive board. The drive board will send signal to the robot car. The robot car will drive from one place to another place based on the best planned path. And this is an iterative process. Everything is captured in real time. We are trying to avoid hitting anybody even if they are moving. So this is basic design of the system. For the methodology or functionality of each component, this is the design of the functionality. We have overhead system just to capture the videos. And then we have the overhead Raspberry Pi system to the video and image processing. It also try to identify the location and map out the environment of the robot car. And then it will try to find the best path, wirelessly communicate the best path down to a ground Raspberry Pi. So the ground Raspberry Pi will do the path tracking and drive the motor to actually move the robot car. So this is the entire flow of the functionality design. In terms of the hardware, we do need a camera, right? So here we mentioned the overhead camera. We do need a camera. We also need 2 Raspberry Pis. So one Pi board is overhead connected to the camera. Another one is on the ground. It's connected to the drive board. And the drive board is further connected to the robot car system. So we can actually do the controlling. Some more specifics of the overhead camera system. So we have the mini camera, because this is just for the lab environment. We are trying to develop a pilot system. It's not in real application yet. In this phase, we think this one is sufficient for our purpose. It's a mini camera, which is relatively cheap, about $15. It has a very high resolution, which is more than sufficient for our application. Like for a video resolution, it's 1080p. If you are just taking the pictures or photos, the resolution is even higher. And its size is very small. I think this is just a little bit bigger than a fingernail. And it is equipped with the functionality of infrared filter. But at that time, we didn't use infrared capability. So maybe in the second phase or third phase, we'll plan to integrate that capability as well. And after that, we have the angle of view, field of view. These are some important parameters. Fixed focus, maximum frame rate, 30 frames per second. That is about 30 hertz. Actually, during testing, we actually reduced this one to about 10 frames per second because Raspberry Pi has limited computing capacity. So if the frame rate is too high, it may not be able to actually process everything in real time. So we have to reduce this one. But 10 frames per second is good enough for our surveillance purposes in this application. As I mentioned, we need 2 Raspberry Pi boards. So this is what the Raspberry Pi board looks like. The most important component is actually here, the GPIO pins, general purpose inputs, output pins. You can set the voltage like to high or low, and then it'll, based on that information, you receive or send the signal to another outside devices. It can also connect to the internet using Ethernet cable. It also has, I think, 4 USB ports. You can connect to the keyboard, the mouse, and also there's a sound port. Camera is just plugged into this port. And we have dual monitor capability. So that means if you have two monitors, you can even connect it here. This one is power. You can also power that through one of those several of the GPIO pins. And you also need to install the software system. The software system will be an operating system, will be the processing, like image or video processing software like the TensorFlow or OpenCV. I'm going to introduce a little bit later. Everything will be inserted into this SD card. We can also use USB drive to put that here, USB disk. That will do the same thing. These Raspberry Pi are relatively cheap. It's just like a very simple computer, single chip computer. So each of these Pi is about $40 when at the time we bought those. And we use the Pi version 3B plus. Nowadays, I think 4B is already out. So their processor and RAM number could be higher. So depending on the cost, this one is probably much better than Pi 3B. And we also need to buy a micro SD card. So for micro SD card, as I mentioned, you have to plug that into the other side of the Raspberry Pi to make sure all the software environment is set up. It can provide Wi-Fi information. So this Wi-Fi transmission is what we actually used in our lab testing. I think I almost mentioned all the things here. So this is the Raspberry Pi. The size of the Raspberry Pi is just like a credit card or debit card. So it's not that big. Before we carry out the autonomous navigation task, we actually bought this toolkit with many different type of sensors, like temperature sensors, moisture sensors, vibration sensors, infrared, and also accelerometer. And we have done some testing using this sensor to make sure we understand how these GPIO pins work. So this is actually a lot of fun during the testing phase. This is during the testing phase, the student is mainly trying to understand how these GPIO pins work and how to connect the GPIO pins with the entire system. For the software, we also need to install the operating system, as I mentioned. Previously, it was called Raspbian. Now it's called Raspberry Pi OS. We can use a different type of software to write the operating system into the micro SD card. And then you insert the micro SD card to the Pi board, it will run. After you boot that, this is how it looks like. And we also have to install the Python 3. I think at that time we're using Python 3.7. I think now Python 3.9 is already out. You can install the latest version. We connect everything through the virtual desktop. So that means we don't have to have a real keyboard connected to the Pi. We're just using the IP address and try to do the programming through the virtual desktop. So that is more convenient for the student to do the debugging. And for the communication between the overhead system and the ground system, by using a protocol called MQTT or Mosquito. This one is very popular for Internet of Things or IoT development in many applications. It's relatively robust, relatively reliable. It can be used to do the communication between multiple sources and multiple destinations. So this one is also lightweight. So that means it doesn't consume so much energy. So this one is the communication protocol we chose. For this computer vision capability, we just use OpenCV and TensorFlow. It turns out during the installation process, OpenCV would take you a lot of time. TensorFlow, you have to use a customized version for Raspberry Pi because the original one probably it will not be able to install on the Raspberry Pi. At that time, we use a light version, TensorFlow Lite. OpenCV, you have to compile that from the source code, which take you maybe several hours. Or if your computer depending on how fast the Raspberry Pi is 3B or 4B. 4B will probably be faster. But this one actually takes a lot of time, and sometimes it's error prone. You have to learn some basics about the programming, and also you have to understand how the compiling process works. So after that, this one, you will install all these different types of software into the Raspberry Pi. So this one is used for, excuse me, this is used for overhead system only, because we do not need to install the software into the ground Raspberry Pi for now. So for this one, we just install that for the overhead Raspberry Pi to provide the computer vision capability. And next, this is a dry board. By the way, all this software system is free. You don't have to pay anything. You can just download that from the website, then install everything, and then that's it. This is another piece of hardware dry board. This dry board is customized at the time we bought the robot car. So the main purpose of this dry board is that it will drive the wheels, the 4 different wheels on the robot car. So it can move forward, backward, left and right, start and stop, and so on and so forth. It can also have infrared sensor interface, but at that time we didn't use infrared capability. Infrared will provide you the capability to see things in the darkness. For example, provide you with night vision, or it will detect different type of temperature differences of objects. So that is about this dry board. And the robot car system is the most expensive piece. And the size of this robot car is just like a shoebox. It's less than 1 kilogram. And then we have the internal power supply, which is this lithium-ion battery. This battery can power the robot car for driving for like a few hours. And wireless communication, it is equipped with Wi-Fi capability, so it can transfer data about 150 megabps. So this one during our testing, it's more than enough for our testing. But in real industrial environment, maybe you probably can use 5G, which will give you maybe much higher transmission speed. And the signal can transmit about 80 meters if there's no block. However, if there are some shelves or some walls in between, the signal will be reduced. So it has 4 motors, a chassis, and also 4 wheels. So this is the basic setup of the system. After I introduce all the hardware pieces and software pieces, now it's time to connect these hardware pieces to make it work together. This is Raspberry Pi. This is the camera. The other end of the camera just plug into the Raspberry Pi camera port. So this is after assembly. This is how it looks like. We do have some keyboards, monitor, and also at that time we actually use USB drive instead of a micro SD card. They are exchangeable, I would say. And this one is a system you would mount on the ceiling or very high location to shoot downward. You can capture the broad view of the ground scene and what is going on the ground. The connection of the robot car, dry board, and Raspberry Pi is relatively complex. So we have to read the manual, understand how everything works, and connect those pins correctly. So this is the Raspberry Pi, this is the dry board, and it is connected to some of the servo on the chassis, and also is connected to the battery, lithium-ion battery, to provide the power. After we rearranged all these cables, this is what it looked like on the ground. So this is the final assembly of this entire system. For the communication between the overhead system and also the ground system, we are using the MQTT protocol, as I mentioned. For the MQTT protocol, we do need the IP address of these two pipeboards. We assume everything is connected through a Wi-Fi environment. We didn't list the router. We just assumed that the router Wi-Fi environment is already there. We're using the internal internet IP address. And MQTT will just send the topic and payload. Topic is something you can differentiate different type of message. Payload is the content of the message. So in this case, we just tested different type of random paths. Let's say the coordinates X, Y, Z. We don't have Z because this is three-dimensional. We just have the two-dimensional, just X information, Y information, and also a series of X and Y information. So these will be the waypoints. Payload is actually the waypoints specific information. And after we send that information to the ground system, we actually received on the Raspberry Pi on the ground. So these are exactly information as we sent. That means communication between the overhead system and the ground system is perfect. There's no flaw. And here is some further testing. We try to understand how to control the movement of the robot car. As I mentioned, everything we need to do that from scratch. So that means the student have to learn from the very basic about these GPIO pins and which one could be like a high voltage or low voltage. So based on that inputs, you will control the car to move forward, backward, left, right, or even backward left or backward right, and also brake. So this is controlled by a student. The car doesn't have any intelligence at this moment yet. But that means we just the communication, wireless communication is working. The movement of the car is working. And we need to make this car more intelligent so it can actually avoid the obstacles by itself. So that will be the next task. I want to mention that this robot car does have been equipped with a small camera on the ground as well. For the first phase, we didn't use ground vision. We only use vision from the overhead camera. But in the second phase and third phase, we're trying to implement and try to integrate the ground vision as well. Now it comes to the autonomous navigation part, which is actually the core of this entire project. So we try to give the intelligence to this system. We need to go through 5 different stages, like image or video processing. This one will be able to identify different objects on the ground and also where the robot car is located. And then it will try to map out the location of the robot car and also its environment, all the different type of obstacles. Based on that information, it will try to plan the best path or maybe the shortest path from one place to another place, avoiding all these obstacles. And then it will try to provide the path tracking to make sure the robot car is actually passed through all these waypoints we planned. So for the first step, image processing, we tried using OpenCV to do the recognition of the obstacles on the ground. This one actually doesn't work. I'll try to tell you some of the lessons learned later at the end, but this is something we have tried. We try to see what will work, what will not work. So that is one of the first things we tried because we read the student read a lot of manual about it. OpenCV. It has very good capability of identifying different shapes and edges of the objects. So we have used the different functionality like canny edge and contour discovery to go through these 5 different processes. Pre-processing, binarize the image, do the edge detection, and also contour recognition. Finally, try to identify the target. But you can see that this one doesn't work so well. The reason is that when we did the testing, the student just put some A4 sized white paper, glue that on the ground to provide a very clean environment or clean background. So this is what she did, but as a result, you can see that there are some patterns, like the horizontal line, vertical line, because of the overlapping. This pattern will interfere the recognition accuracy of OpenCV. Another thing is that there is also lighting issues. You can see that there's some shadow in certain area, and the lighting condition is not even. So that is another problem that caused the inaccurate detection. It can detect two objects correctly. Like this one is a black bag. This one is a gray plastic case. This one is a plastic, I think, box, and this one is a coffee mug. You can see that you can identify these two objects, but for these two objects, it missed due to the interference with the shadow with a different type of pattern. So this one doesn't work so well. And then we turn to another package like TensorFlow. We try to use deep learning capability to do the training and to see whether this one will work or not. The basic principle of this TensorFlow is that you have to have a lot of training data. So if you're using this one to create a self-driving car, maybe you have to identify different type of other cars, like a sedan or a Jeep or SUV or a motorcycle on the ground. And based on that information, they try to generate the different type of features using deep neural network. It will happen automatically using some of the algorithms there. It may identify different features like how many wheels you have, what is the color of the wheel, what is the shape, does it have any glasses, and so on and so forth. So such information will be extracted, and then it will be inputted into a neural network, and with all these labels. This is supervised learning. And after that learning, it will be able to identify, okay, this is a sedan, or this is a motorcycle, and this is actually our robot car. And you use testing data, new data, input into the entire system, and it will go through the same feature extraction process. And after that, it will tell you whether it's a robot car or not with a certain number of confidence level. So this is a process we have gone through. For our training, we just train that using some objects commonly seen, or we assume that will be there on the ground, like boxes or pallets. If you are dealing with a real warehouse environment, you have to train that with real objects from the overhead view, like maybe a person is moving by, forklift truck, or maybe pallets or different type of totes, or shelves. That kind of information, you have to use those to do the training. Now, for the image processing, the student just did some experiment in her apartment because at that time she was performing this task. It was a COVID-19 situation, and many of our university labs have been shutting down, and many of the businesses in the local area have also been shutting down. So she just did the experiments in her apartment. She actually took several hundred pictures of this robot car, and with different background. Maybe sometimes there are just one object, other times there could be multiple objects in the background, and with different lighting conditions, different angles. The main angle is trying to shoot that from the top view. So that means we are trying to look down using a camera that is mounted on the ceiling, so to simulate that kind of a real world situation. This one is a robot car and several boxes and even shoes in the background on the floor. And this one is on the table. This one is on the carpet. This one is, I think, is a chair, most likely. And we did reduce the image to 800 by 600 for faster processing. The training process will take you a long time, and also even the testing will take you some time after the training is done. Because Raspberry Pi doesn't have very strong CPU, and it doesn't have any GPU. So that is why we have to reduce the resolution from very high resolution 1080p to 800 to make sure we can process the information in real time. And this is what we did. Later, we find out even we make this color image, like RGB image, to gray image. So that means everything will be black, white, or gray. That will also work. It seems like that will make the entire system much faster even. For the image processing, we actually used this one to do the labeling. So this is called label IMG. This is very popular open source software you can download from the internet, GitHub. And this one, the main functionality is listed on the left column here. And what we did is that we take those photos we shot and put that into this, load that into this software. And then the student has to manually draw the boxes to bound the objects locations. So for each of these objects, she has to do the drawing manually. Because these objects are not seen by TensorFlow existing weight, so we have to do the training all by ourselves. I have to identify the robot car location, some big box and a small box. For each of them, you have to give them an appropriate name. If we have more different objects, you can give the different more classes. Here, we just tried 3 different classes to see whether this concept will work or not. So this is basically a proof of concept project. After you have labeled everything, you can save this file into your computer using the XML file format. You can see that we have already trained, so we have already labeled many files in the computer. So after that step is done, she has trained all these hundreds of images. All the information is stored in the computer. And she split the training and testing data into like 80%, 20%. So this is a typical split in many machine learning algorithms. After that, she created a training profile, like how many classes you have to detect, like how many different type of objects. In this case, we just use 3 different type of objects, like the big box, the small box, and the robot car. Of course, you can have more, like shelves, toads, pallets, and the people even. And then we specify the training and testing data location from the computer, so it can actually find those files when the training process begins. And after that, we pick one algorithm, faster RCN inspection version 2. So at that time, the student picked this one. Of course, there are many other algorithms we can try. A YOLO framework is also a very popular one. I think nowadays a lot of people are using YOLO to detect cars on the street, to detect different people, different type of animals, or even different type of commonly seen home objects like chairs, tables, and so on and so forth. So this one is changeable. You can actually change that to some other things. TensorBoard is a tool we use to monitor the training process. Basically, you want the loss function to be as small as possible. So that means you try to reduce this loss to 0, but it will never reach 0. After a certain number of iterations, we just stop training. So we just assume this one is satisfactorily trained. After that, it's time to test all these algorithms and try to make sure you can actually identify different type of objects. So here we did some more photo, took some more photo and try to identify. This one is on the ground. We have the robot car correctly identified. We didn't train the bananas. We didn't train the chairs. We didn't train other boxes. But if we did, we will be able to identify those objects as well. This one is another one. So we have multiple objects on this scene. We can also identify these objects correctly. And even if they are crammed together, so we can still identify these objects. So the testing phase shows that this algorithm is actually working after training. Next step is try to map out the entire environment, try to get the coordinates of the boxes of the robot car to output some information like this: the X information, Y information at the top left corner for each bounding box, and also X max, Y max. That means the bottom right corner. We try to find this bounding rectangle for each object. And for the robot car, so this is correctly identified as a robot. This one is correctly identified as a box M. This one is identified as a box A. That means you can correctly locate those objects and map them in the environment. We also did more testing like this. After we identify the object in the map, we tried to use a black box to represent that this is the area we cannot go through. So this is some occupied area. So if the robot car is trying to go through this area, it's gonna hit the obstacle. So this one is marked as restricted area. You can also identify the center of the robot car in the map. Of course, you have to consider the size of the robot car and also the distance, and also the size of the available space to see whether the robot car can go through this space or not. So everything is done by TensorFlow. I find this one is a very convenient tool. Of course, there are many different algorithms you can try, and you can even develop your own algorithm to make the accuracy higher. And we have done more testing using different type of setup. The box is here, or they are connected together. So after the running of the algorithm, we can correctly identify the location. So this will be marked as blocked area. Cannot go through those areas. Now, after the location mapping, it's time to plan the best path. And based on the information of the obstacles on the ground, you have to plan where you should go, which area you should avoid. This is a basic illustration of the path planning if there's no moving obstacles. Basically, you try to find the shortest path from the one place, the starting point A, to the destination B. There are several different types of algorithms to do that. We have tried these two, Dijkstra algorithm and also A-star algorithm. These are very classic, very typical algorithms we can try through for this path planning. Dijkstra algorithm, the advantage is that it can find optimal paths from the starting point to the final destination. This is how it works. It's very similar to when you are throwing a stone into a lake. You will see the water wave moving forward to every direction in the same speed. After it hit a wall, it will bounce back and try to find other locations. Finally, it will reach this destination. And based on the destination it try to find the best path. The problem with this algorithm is that it's very slow, especially for a very weak Raspberry Pi computer. It cannot work for us to reflect the real path for the moving environment. So for example, if people are moving here and you find one path, before you find the optimal path, people already moved to other locations. So that means those blocked area can actually change. So this one will not be able to actually satisfy our real-time application purposes. A-star algorithm is a little bit better than this one. So in A-star, it's also very similar to when you're throwing a stone into the water, but the wave is transferring to the direction with promising optimal paths in a much faster direction, much faster rate than to other directions. So this one is much faster compared to the dexterous algorithm. But this one will never guarantee to give you the optimal path. So it will give you a satisfactory path with very short distance, but this one is probably not the shortest. But anyway, this one will provide a much faster calculation. So we just decided to use this A-star algorithm when we did the testing. Actually, there are many other path planning algorithms. For example, nature-inspired algorithm like genetic algorithm, taboo search. You can also use particle swarm optimization. These algorithms have the similar property of A-star. They are meta heuristic. They cannot guarantee to give you the optimal one, but they will give you the good solution in very short time. This is actually the testing based on our real scene, like when you have blocks in two different locations, and you have the starting point. This is the end point, and how do you when you apply this Dexter algorithm or A-star algorithm, you can see the A-star algorithm will take much shorter time iteration to actually get to the optimal point. Next step comes with path tracking. This one we're trying to control the movement of the robot car, so it will follow the path we have planned. So we have tried two different types of controlling algorithms. Model free, that means we do not consider any dynamics or kinetics of the robot car. We just use PID control to see whether it deviates from the planned path or not. If the deviates is very big, then we try to control the wheel to the opposite direction. We did the testing, but it turns out this PID control is not very good. The performance is not very good for our application here. And then we tried some model-based steering control methods, like this pure pursuit control. This is the simplest one, probably. We tried this one. It works much better, and we have decided to just use this one. The limitation of the robot car is that it cannot control separate wheels. When you send a signal like turn left, all the wheels will be controlled at the same time. So we cannot separate control this wheel. Due to the limitation, we cannot try these two different algorithms. But if you have a very fancy car or a better robot car, you can even try model predictive speed and control. So that one probably will consume more computing power from the Raspberry Pi, but will provide you more accurate control. So this is a pure pursuit algorithm we have tried. First of all, we try to do the simulation to see whether we can go from one place to another place using simulated paths and waypoints. So these are two blocked area, and then we have the starting point here, end point is located here. The red path is actually the best path we found using the algorithms. You can see that this is a dynamic animation. The red path is the best planned path, but you can see that we have very sharp curves, sharp turns. In reality, the robot car can actually turn like exact 120 degrees or exact 90 degrees. The wheel must turn very smoothly. So this is the actually simulated path based on the control, pure pursuit control. You can see that it smoothly transfer or try to follow the waypoints one by one, and then when it turns, it will never exactly follow those 120-degree turn. It always smoothly transfer to the next waypoint, and finally go to the final destination. The simulation seems to be working. And after we done the simulation, we also carry out this experiment in the ground. This is still her apartment, the floor. You can see that we start from here. We try to go to the next waypoint. Let me see if I can play this video again. And basically it goes to that direction and horizontally, and then turn left again. So it seems it's following the planned path This one, nobody is controlling the car. It's just controlled by the overhead cameras. So now the car has some kind of intelligence. One thing I want to mention is that for this cable, this is just the power cable. During some testing, we actually burned some very important component in this robocar drive so that is why the battery cannot be connected to the drive anymore. So we have to supply the external power to this robocar so it will move. So let's say if there's no problem with the drive then we don't need this external power line. This is another lesson we have learned during the development. So this is one more testing. We also simulate this kind of environment with two boxes together. And after that, we have the simulated results. And also we try to do the experiments later to see whether this line can be connected to a different location. And this is simulated results. This is the actual results. You can see that the things are moving from one place to another place. And now, again, it's not controlled by the student. It's just controlled by the overhead camera. And it's moving horizontally and then gradually turn and then to the final location. So overall, to summarize this research, we have carried out this work using all the hardware and also software combination to make sure the entire system is working. So this is the first prototype. It's far from being perfect at this stage. Some of the lessons we have learned. The first thing is that when the robocar is moving and it may vibrate, and at that time we just loosely connected the cables to the GPIO pins. You can see that somehow the wire got shorted and it burns and smoke came out. And also after it burns, this wire turns black and it actually burns some component in this drive board. As a result, we have to replace this drive board. But during the COVID-19 situation, the manufacturer is actually out of stock. So they don't have the exact same drive board at that time. And we actually bought another one, which is similar, but not exactly the same. So that is why we cannot connect the power cable to the battery. So we have to have an external power cable. The lesson learned that maybe next time we should solder all these joints together instead of just loosely connected these pins. So that will make the entire system more robust. Another future work we're proposing is that in the future, we may also implement the ground vision. Right now, we are only relying on the overhead vision computer. This is just one simple camera. The ground vision may provide you redundancy. For example, when the wireless communication went out or the wireless communication is not so reliable, it may lose some of the information during the transmission. So if you have the ground camera or maybe ultrasonic sensor, which is also equipped in the robocar here, it can provide a lot of more realistic information and real-time information. So we can avoid hitting moving objects as well. So that is actually in our plan for the next stage. We have done some initial testing using OpenCV's edge detection. For example, I think this is still the student's apartment. We have sofa, we have doors, we have walls, we have boards, and she just placed some toy cars on the ground, on carpet. And based on the OpenCV edge detection, we try to see whether we can detect this distance from these robocars. The red line marks the distance, marks where the object is, obstacle is. So it seems like it can correctly identify those obstacles. Of course, there are many coding and debugging to do in the future to make this one a little bit more robust. Ultrasonic sensor can also be used to avoid short distance collision. Another type of future work is that we try to expand from this one camera, one robot car system to multi-camera and multi-robot car system. Imagine a very big warehouse. You have a very large area to cover. So each of these camera can only cover a very small area. So let's say if you have a grid of these cameras in the X and Y direction on the ceiling, they can probably cover the entire warehouse. The benefit of this redundancy is that if one camera view is blocked, let's say there is a very tall shelf, it's blocking the view of this camera. This camera can somehow capture that part that was blocked by the shelf. And with that kind of redundancy, we can do the planning from the one place to a very far away place. Basically, these cameras will relay all this information, so the robot car can get to know where to avoid, where is the best path. They can also do the path planning and the mission to carry, for example, one box from one place to a middle place. And then another robot car will just carry that from one place to the final destination, and so on and so forth. You can do a lot of this interesting study about the operation research, path planning, how to route different type of vehicle for different missions. So this is another future work. I think that's pretty much all the information I would like to provide. But I think I have one short video about the Binghamton University. I'm not sure whether everyone is familiar with Binghamton University. Maybe some of you are familiar with our university. Many others don't, are not familiar. I have a short video. It's about 4 minutes. Let's just play this short video.
This is a place where bright minds meet.
Can everyone hear the voice of the video? Okay, I'll just play the video.
A world-class institution with renowned faculty, endless opportunity outside the classroom, and a tight-knit community. This is Binghamton University, the premier public university. Binghamton is located on a stunning 930-acre campus, nestled in the wooded hillsides of upstate New York. People at Binghamton affectionately refer to the campus as the Brain, a reference to the university's unique layout. But it's not just a neat nickname, it's a constant reminder of our pursuit of knowledge and understanding. And at our 7 different colleges, that pursuit of knowledge is tailored to each student's personal passions. Follow the green paw prints and you'll end up at the state-of-the-art admissions center, a one-stop shop for students. More than 30,000 applications make their way through the center's doors. Put simply, an acceptance letter from Binghamton is something to be immensely proud of. Binghamton University is a home for living and learning. More than 7,600 students reside in the 6 residential communities that outline campus. Ask any student which residential community they live in, and they'll likely well up with pride. Community is key at Binghamton University, and each residential community offers a unique and enriching living experience, one that enhances the academic experience and reinforces an atmosphere of camaraderie. Career development, mouth-watering food, bowling, billiards, and more. The University Union has it all. The Union is a center of information and entertainment for Binghamton student body. Binghamton University offers an incredibly diverse range of classes, from film theory to tree climbing to the physics of materials and everything in between. You'll find these classes spread out over campus with traditional classrooms, ultra-modern laboratories, and even classes in the great outdoors. Research is big at Binghamton, and the Innovative Technology Complex is the university's research hub. Here, leading scholars work together with student researchers to push technology to astonishing new levels. From stunning visual arts to stirring theatrical performances, our school supports a strong community of artists working in a variety of media. fostering artistic growth and offering year-round enrichment and entertainment. You'll see plenty of Pantone 342, the university's official color, when you come to campus. We have a proud tradition of supporting athletics at Binghamton, and with 21 Division I sports teams and a devoted student fan club, there are opportunities for athletes and spectators alike. Do Kung Fu, badminton, or ultimate frisbee sound like fun? These are just a few of the 40 or so club sports Binghamton students get to choose from. Students also have access to FitSpace, a 10,000 square foot fitness center where swimming, fitness classes, and new equipment make staying in shape no problem. Within our campus lies a 190-acre nature preserve featuring a 6-acre pond and trails for biking, running, and hiking. A hotbed of biodiversity, this space also offers real-world research opportunities. The University Downtown Center, located in the heart of downtown Binghamton, is home to the College of Community and Public Affairs. Through professional research, civic engagement, and public service, students here find a practical way to change the world. With a beautiful and bustling campus, incredible research opportunities, a spirited and diverse community, and a continual commitment to excellence, Binghamton University is truly the premier public university.
Okay, I think that's all my presentation. Thank you very much. Any questions?
Thank you, sir. Yes, sir, there are a few questions. Before that, I would like to thank you for the wonderful and informative session. We are all highlighted on how to use a Raspberry Pi for navigation of a robot car. And even thank you for introducing the Binghamton University for all of us. So before we conclude the session, there are a couple of questions, sir. Can I just convey it to
Sure.
you?
Yeah, please.
So what are the things to be kept in mind while designing low-cost video communication system?
Okay, yeah, that's a very, very good question. So when we try to develop this low-cost system, our primary concern is actually the cost, right? So for this one, we only had a budget of $200 something to buy all the hardware. So for this one, we have decided to do some searching on Amazon before we design the entire system. Because Amazon is probably the fastest or most reliable location we can find this cheap, low-cost hardware, like this camera, these Raspberry Pis. I think, first of all, you should be able to understand the scope of the project. So that is the most important. Based on that scope, you can maybe have some initial design. Whether this design will work or not, you don't know. And then the student actually talked to me, like we have gone through many different type of prototype, many different type of design. So this is a final design. Previously, we also tried to think about using more fancy hardware, for example, using NVIDIA, Jetson, that kind of a computer that can provide much higher capability. They have maybe stronger CPU and also maybe some of the GPU capability. But due to our limitation on our budget, we cannot buy those hardware systems. But if the budget is not a major concern, I think maybe you can also try those systems as well. So here, based on our design, based on our requirement, also the budget consideration, and also the scope of the system. So this is the entire system that came out. So this is our thinking when we carry out the design of the entire system. Low cost is always our concern. So that is why we are trying to be practical and also make sure everything will work. I hope I answered your question. Yeah.
Yes, sir. So there is one more, sir. Like how effective the system is in handling obstacles and uncertainty.
You're probably talking about the moving objects, right?
Yes,
so
sir.
uncertainty, that means if people are moving and the environment is constantly changing, whether the system will capture that information or not. So for this one, we didn't do the testing. You can see that for the testing at the end, we only tested in our apartment At the time, she's the only person in her apartment and did all the testing. There's no moving objects around. The overhead camera, I think it can capture the moving object because we are using 10 frames per second. The processing speed, I don't think there's a very big problem. It's just that at that time we didn't do the testing. But in order to make sure the entire system more robust, for example, if there's no Wi-Fi transmission in the environment or the Wi-Fi transmission is not reliable, you cannot extend the information on planned paths from the overhead camera to the robot car. It must rely on some ground system as we proposed in the next phase. Probably it's the best idea to use the ground vision as well, and maybe ultrasonic to be equipped with the entire system as well. So that is our plan for the next phase. I think this is definitely a very good question. For the dynamic environment, maybe more things, more missions should be accomplished.
Yeah. Okay, sir. I think the answer is being conveyed. And there is one more question, like how effective the system that is done. So how we can foresee the future of autonomous vehicles?
That's a very big question, right? I think autonomous vehicles nowadays, there are already many big companies like Tesla, Waymo, even General Motors, they bought some startup called Cruise. I think Indian company like Tata is also researching their own autonomous cars. All these companies are spending like millions and millions of dollars recruiting people and try to develop. Their final goal is level 5 autonomous cars. Everybody is spending a lot of money and spending a lot of like talents in this area. But right now, I think different companies are taking different routes. For example, I know that Tesla is directly selling all these cars with autopilot capability. Recently, they also try to upgrade the capability to full self-driving. Some kind of software is developed. They can be downloaded, but you have to pay a certain fee. So you can actually enjoy all this autonomous capability. Waymo is taking another route. I think they are testing 600 or 700 different type of taxis in different cities. I know in Phoenix, Arizona, they are testing all these taxi services. Based on that information, they try to collect a lot of data and try to make their system better. I think definitely autonomous cars will be the future. I just don't know whether this will be 5 years or 10 years or 20 years. Before that, I think electric cars probably will hit market earlier than these autonomous cars. I think most of these autonomous cars should be electric cars. Nowadays, electric vehicles is only about 2% market share in the United States. I don't know about India. I think some other countries playing a very big role, like China. I think they are making this initiative, try to encourage a lot of people adopting electric cars. After all the technology is there in the future, I definitely think you will see more and more autonomous cars on the road in the next, let's say, 5, 10, or 15 years.
Okay, sir. So there is one more, like, is any mapping technique required to compare the trained data with real obstacle?
Let me see if I can understand. In the mapping algorithm, let me see. So can you repeat the question again?
Sure, sir. Is any mapping technique required to compare the trained data with real obstacle?
I'm not sure I have the answer to that question. I think this is also a very good question. So for the mapping, I think the basic idea is that you try to find the coordinates and try to make the autonomous car understand its environment. So if it cannot understand its environment, it cannot move, right? So that is the main purpose. So here, what we did is that for just using the camera, we're trying to provide some kind of a GPS information. So if you are outside in the open road, you can use GPS to locate where you are, and you can use different type of sensor to identify your environment. Here, we're trying to just use the camera to serve for indoor applications, because the GPS information, of course, is not accurate for indoor application. We're trying to use camera to provide some kind of overview to make sure that the car knows where it's located and where its surroundings, what are the obstacles in its surrounding environment. There could be some other mapping technology using maybe Wi-Fi, using RFID, using maybe some other ultra wideband technology to do the mapping as well. I think camera is the way we did. It's just like a Tesla and Waymo. They are taking different approach. Tesla is against using LiDAR. They are just using cameras and ultrasonic. Waymo is using LiDAR, ultrasonic cameras, everything. So this is some kind of proof of concept idea. Again, we're trying to do the testing to see whether it works or not. In the future, of course, there could be a lot of things that can be improved.
Okay, so those were the few questions, sir. I think there are no more questions. So with your permission, shall I conclude the session, sir?
Yeah, sure. Thank you very much. It's really my honor to be here and try to, I really enjoy these talks and try to collaborate with maybe many of the faculty member colleagues at MIT. It's really my pleasure. Thank you, everyone.
Thank you very much, sir. In spite of your busy schedule, you have given your valuable time for us, and we would all like to thank you on behalf of all the participants and behalf of organizing committee from Mangalore Institute of Technology and Engineering for this wonderful, interactive, and informative session, sir. Thank you, sir.
Thank you. Yeah, it's my pleasure.
Thank you, sir. Thank you very much.
Okay, have a good evening, everyone. And I'll just log off. Thank you.
Thank you. Have a good day, sir.